Alright, I'm going to go over section 6.2, volumes of revolution. So we know how to find the area under a graph from integration. Volume of revolution is just turning that two-dimensional area into a three-dimensional shape by revolving it around an axis of revolution. That creates a cylinder shape with the disk method, like that. And we find the volume with the equation. And then the area would be pi times the function, because function squared, because say the x-axis is the axis of revolution, the function would be the radius, and this slice right here would be essentially like this of the cylinder, and the area of a cylinder is pi r squared, and you just replace r with the function because it would be the radius. And that's basically using the disk method to create a volume from an area. And then I'm going to go over an example of this. An example would be rotating the region bounded by the equation square root of x equals 0, and x equals 1 about the x-axis. So first you draw out the region. So that's going to be our region rotating around the x-axis right here. And I'll rotate around, creating a shape such as this. This two-dimensional area will create a three-dimensional shape similar to that. And then to compute that would be y equals the boundaries of the area, and then ax dx, and that would be pi r squared dx, and then r would be the function dx equals pi of square root of x squared. And from here you can pull out you just integrate it. So you pull out pi, gives you squared, that gives you x. Oh, I forgot the dx in these, sorry. Where we left off was x dx, and the integral of that would be pi times x 2 divided by 2 of 0 to 1 equals 1 squared minus 0 squared. So then your volume would be pi over 2, given those boundaries. You can do this around the y-axis or the x-axis, or the y-axis, or like any line given in the description that is similar to the y-axis or the x-axis, such as like x equals 2 or y equals 2. Those can also be axes of revolution. But if it's around the x-axis, you simply change the variables to y. So the equation we used in that example was the square root of x, and then you just change it to x equals something, the variable of y. So then it would be y squared if you were doing it around the y in the parameters. Oh, now I'm going to be giving an example of all using the disk method around the y-axis. So 2 would be volume of the solid from revolving the region bounded by x equals squared on the interval 0 to 1 and the y-axis about the y-axis. So again, you draw out your region. So this here would be our region, and we're revolving it around the y-axis. So again, it gives us a similar shape before, but it will be standing upright, like that, sort of. Y-axis right there. Like I said before, you change the parameters of the equation to variables of y. So then y equals x squared would then be x equals square root of y. And same as before, instead of x intervals, you will be using the y intervals. So it would be still 1 or 0 to 1 pi times r squared dx, which is pi times root squared dx. You can take out, it's the same equation basically, but with y. So I'm just going to speed this up. Equals pi 2, 0, 1. And you get, again, the area, the volume would be pi over 2. And that's how you do the disk method around the y-axis. Oh. You can also find volume of revolution using the washer method if there's a space, and I'll explain that now. Say I was revolving this region right here around the y-axis. There would be this unaccount for space that creates a cylinder inside the bigger cylinder that has to be accounted for. So it's basically the same as the disk method, except it's the outside subtract the inside cylinder, and the resulting solid would be something similar to this, with this like empty space in it, and then the cross sections would be washers, and that's why it's called the washer method. And like how I explained earlier, of like the bigger circle subtracting the bigger cylinder subtracting the inner cylinder, that's how you also solve it. So it's similar to the disk method, in where you find the volume of a cylinder, which is pi r squared, but instead you are accounting for the inside cylinder as well. So then you're going to be subtracting, using the big R would be the outside radius, and then the little r will be the inside radius, and you're taking the volume of the bigger cylinder and subtracting the volume of the little cylinder inside. So I'm going to give an example of this. Volume of solid formed by revolving region bounded by the graphs y equals square root of x minus 1 and y equals minus 1 squared about the x-axis.